So, good evening, everyone. I'm Calvin Joseph, and today I'll conduct your problem solving and doubt clearing session for the NPTEL course, Digital Electronic Circuits, and we will be considering for the week 6. So, in the week 6, Sir has covered various important topics such as uh, digital comparator, okay, or digital comparator. Next, he has also considered arithmetic logic unit. Arithmetic logic unit, also known as ALU. Okay. Then he has also taught about error correction and detection. Error correction and detection. So let's considered unweighted codes. What are unweighted codes and what is their significance? And why do we go for that? As well as binary multiplication and division. Okay, these are various things which Sir has considered, and we will look into it briefly, and we will try to, understand and solve certain previous year questions so that we are well equipped to tackle this week's assignment questions. Okay. So, what is a digital comparator? That is a magnitude comparator. So, what does it do? It will have two inputs. So here you have your comparator. It has the input A, the input B, and it will give three outputs. One is equal to, one if it is greater, one if it is less. Greater when A is greater than B. E is when A is equal to B, and L is when A is less than B. All right. So initially what people did was, or what Sir taught was, you can just do subtraction. Subtraction of A and B. Okay. And then one must check the MSB. So if the MSB is 1, means the number is negative. That means A is less than B. If the MSB is 0, then it could be either 0 or positive. So the condition becomes A is greater than or equal to B. This is the condition. Okay. So for this, what the approach was, you had to do the subtraction. You need a subtractor circuit. And after that, you have to check the MSB. It is very complicated and we do not need to do subtraction. So that's why Sir told us a different circuit, which will just is optimized, made for the specific application of comparing. Okay, you are just comparing the magnitude of two inputs. Okay, so let us have the truth table. So let us say we have X here, Y here, and this will give whether it is greater, equal to, or less. Okay, there are two numbers. Let us start with 1 bit. 1 bit comparison. So XY 0, 0, 0, 1, 1, 0, 1, 1. So if X equal to 0, Y 0 means, is it greater? No. Is it equal? Yes. Is it less? No. If X is less than Y, so is X greater than Y? No. Is it equal? No. Is it less? Yes. Is X, so this is when X is less than Y, and this is when X is greater than Y. And E is when X is equal to Y. So in X greater than Y in this case, yes. 0, 0. X1, Y1 greater, no, 0, equal to yes, less is no. Okay. So you can get the, what would be the condition. So for G, if you want to find the greater, what you have to do, you have to use X and Y prime. If you want to find equal to, it will be X bar, Y bar plus X and Y. And if you want to find less, it is equal to X and X bar and Y. Okay, so this is the truth table which you can use and you can generate the required outputs. Now, what about if you have 2-bit magnitude comparison? Okay, you have here x1, y1, sorry, x0, y0. It gives you your G0, E0, and L0. Similarly, you have your x1, y1. That gives you your G1, E1, and L1. Okay, so it is a 2-bit magnitude comparison. That is, our x is actually made up of x1, x0. Our y is made up of y1, y0. And then we have to check whether it is greater, equal to, or less. Okay. So x1 and y1, if x1 is greater than y1, then it is obviously greater. So that means if g1 is there, or if x1 is equal to y1, that is e1, and if x0 is greater than y0, then it is g0. For equal to, it should be e0 and e1 should be equal. And for less, it should be is L1 is x1 less than y1. If that is the case, it is correct. Or if the x1 is equal to y1, then you must check L0. Okay. So this is how you can construct, and you can increase it to any number of bits. Accordingly, you can increase it. Okay, you can have n-bit comparison, you can have multi-level comparison, and various other things you can do. Next, we have what is known as an arithmetic logic unit. ALU. So what it does is it has A, B, C, various inputs are there. Okay. And it has select lines S1, S0, and so on it can have. And it has some output Y0, Y1, Y2, so on it can have. So this might look similar to the MUX multiplexer circuit which you have learned. But what you must understand is that depending on S1 and S0, okay, it could be 0, 0, 0, 1, 1, 0, 1, 1. What you could have Y0, Y1, Y2, and this could what it could be A or B. This could be A plus B. This could be A plus B plus 1. If Y0 is there, it could be A and B. This could be A or B. This could be A XOR B, and so on. So it can perform various arithmetic operation. It can perform various logical operations. It is that one circuit. It's not the one circuit. It's like the one IC chip. It has various circuits within it, which will do various other combinations. But depending on these select lines, you will choose what function, what arithmetic or logical operation you want it to execute. Okay, so it is like it is giving you a range, a wide variety of options which you could use. Okay, so that is the advantage of the arithmetic logic unit. Okay, next you have, let us go to the next page. Unweighted codes. Okay, let us say this is A, this is B, this is your decimal equivalent. So this is your 0, 0, 0, 1. So this is 0, This is decimal 1. You have 1, 0. This stands for 2. You have 1, 1. This stands for 3. So the critical part is this is changing from 1 to 0. This is changing from 0 to 1. Both changes are occurring. And if there's a delay, if there's a mismatch, what could happen is 0, 1 could change initially to 0, 0. Okay, this has changed. Then this will change. Then this becomes 1, 0. So initially the value is 1, then it becomes 0, then it becomes 2. So this temporary portion, this transient portion, it is not correct. Okay, it is an incorrect or a misleading representation. Okay, so that is why to avoid it, they come up with technique where the bits will not change so much. Like, sequentially one bit at a time will change as you will go up or increment or decrement. Okay, another part is this A, B. If you want to find the value, what do? You multiply by 2 raised to 0 plus 2 raised to 1. This is how you get the value. But now if you want to make sure that the bits change only sequentially, then it becomes a little bit more complicated. Okay. So now let this be the decimal equivalent. So this is 0. So that is 0, 0. This is 1. So this is 1, 0. Then you want to change only one bit at a time, right? So this will become your 1, 1. So 2 will become your 1, 1. Then you will change this bit. So this will become 1, 0. So this is 3. Okay, so one bit at a time you are changing. You don't change both the bits simultaneously. That is not at all permitted. Okay, that is not permitted. So to do that, so this is known as your gray code. This is known as the gray code. It's kind of like coded. It's not weighted. You cannot say that this bit means 2, this bit has magnitude 1, this bit has magnitude 2, 1. It's not there. It doesn't have a weight. It is just a reflection code. It is something also known as a reflection code. All right. So this is regarding the gray code. Similarly, there's another code which is known as the XS3 code. This is used for BCD numbers to facilitate ease of addition and subtraction of BCD numbers. You use the XS3 code method. XS3 code representation. So what does XS3 code mean? You have a number. Let us say it is, first it's a BCD number. Okay, a BCD number you have, that is you have 5, 8 BCD. Okay, this 5, 8 in BCD. So if you represent in decimal what it is 0, 1, 0, 1, and it is 1, 0, 0, 0. This is your 5, this is your 8. Okay. But the limit of BCD is 9. 9 limit in BCD is 1, 0, 0, 1. But what, when you do addition, subtraction, the bits will increase, it will overflow. You have to take a 9's complement, 10's complement, various other things were there. So what they do is any number, any BCD number, they add the number 3. You add 3. That is why it is known as excess 3. Excess means more. So that's why you add 3. So now if you want to add 3, what you have to do is the 0, 1, 0, 1 is there. You will add to it 3. That is 0, 0, 1, 1. Similarly, this 1, 0, 0, 0 is there. You will add to it 0, 0, 1, 1. So what will the output be? This is 1, 1, 0, 1. This is 0. This is 0. This is 0. This is 1. So this is 1, 0, 0. And this is your excess 3 representation of 58. This is how you represent the excess 3 representation of 58. Okay. So this is mainly used for addition and subtraction of BCD numbers. It facilitates that. That is why excess 3 code was come. It makes it, symmetric for addition and subtraction. You have to do a certain when there's overflow, you don't have to add like when there's overflow, you subtract 0011. When there's no overflow, you add 0011. All those concepts are there. Okay, so that we will look into it if we get time. Next, after that, you have error correction detection. So you have a set of bits that are say this. Okay. And you have another set of bits that is 11000001. Now you want to have even parity, right? You want to have even parity. So what do you do is this is even, so you add 0, this is the parity bit, and you have 10111010. Here it is odd, so you add a 1 parity bit, and then this is 1100 1 2 3 4 0 0 1. Okay, so this is for even parity. Now parity can only detect corruption of 1 bit. It can only detect corruption of 1 bit and cannot correct it. And it cannot correct it. Okay. So if you want to have a opportunity, the method of correction, then you have something known as Hamming correction. Hamming method of correction, where you will, instead of only 1 parity bit, you will add multiple parity bits at suitable locations. Okay. Yeah. So then also Sir further talked about binary addition, where Sir developed a combinational circuit. What it does, it breaks down multiplication into repeated addition. Okay. Similarly, you can have binary division as well, where you have to use a subtractor circuit. All right, so we'll start solving the assignment questions. So question. So which of the following logic gate can be used to find x equal to y, where x and y are 1-bit binary numbers? Okay. So you need to find a circuit where you have x and y, and you have to have an output. Okay. Since x and y, they are, let us say they are individual bits, they are 1-bit binary numbers. So this is 0 0 0 1 1 0 1 1. So you want to find a case when x equal to 1. So if you will see for AND gate, what is the output? Is 0, 0, 0, 1. So it can, and what do we want? We want to detect this condition and this condition. So AND gate is not enough. So let us select OR gate. OR gate gives 0, 1, 1, 1. So it is still not satisfying. If you see XOR gate, it gives 0, 1, 1, 0. Okay, so we are getting closer. And if you see it XNOR gate, it gives you the correct thing. Okay, so you have to use an XNOR gate for this thing. So XNOR gate is useful for you when you want to identify X equal to Y. Okay, this you can identify using an XNOR gate. Okay. So let us see further part. So what do we have is A1, A0 is 1, 1. This is 1. This is 1. Okay. B1, B0 is 1, 0. So this is 1. This is 0. This is 1. This is 0. So let us see what is 0 and 1 is 0. So this is 0. Again, B1 is 1, 1. So this is 1. Okay. B0, 0 and 1 is 0. So this is 0. Then when you do 1 or 0, you have sum and you have carry. So this is coming as carry. So this will become your 1. And your carry will become 0. So 1 or 1, 1 plus 1 is what? 1 plus 1 is, wait a minute, it is the carry. Okay, so this is your sum. So, and this carry is going. So this will be 1. Sum is 1, the carry is 0. So 0 and 1 is, again, sum is 1 and your carry is 0. So that's why your C3, C2, C1, C0, there'll be 0, 1, 1, 0. Because what is the half adder circuit? This is, let us say, your input A, input B. This is your sum. And this is your carry. Okay, so accordingly. So I got confused, but this is the correct thing. So this is the sum, this is the carry. Okay, this is again the sum, this is the carry. Right? So let's take another question. This is the question. Okay. So you have what is given here. There is a 2-bit arithmetic logic unit, ALU. Yeah. We want to find the, we are interested in, what are we interested in? Y1. Okay, consider the following 2-bit ALU with the given truth table. Find out the minimized expression for output Y1 when input seen is 1. So this is given as 1. The output expressions in truth table are valid for both Y0 and Y1 independently. What is important is the term independently. Example with S1 and S0 as 0, 0. Output Y0 is A0 and B0 prime, and Y1 is A1 and B1 prime. So now we are interested in y1. Okay. And we are interested in the case when Cin is 1. So you have y1. So since Cin is 1, this could also be 1, this could also be 1. We can consider, so y1 is equal to S1 bar and S0 bar into A and B prime. Okay, first, okay, before doing this, let me consider some various things. Let us consider what is A and B. And what is the output y? We are considering y, it is A plus B. Okay, let us interchange it, B and A, so that it becomes easier. So this is B, this is A. Let us just consider. So this is 0, 0, 0, 1, 1, 0, 1, 1. So A plus B is what? A plus B, 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0 and there's a carry. Okay, and with one carry. What will be A plus 1? What is A plus 1? A plus 1 is this case. This case. When you do A plus 1, what do you get? You get, this is not considered. Okay, so A plus 1 means B is just replaced by 1, which is this. So this is again 1, 0. So A plus 1 is actually equal to A bar. A plus 1 is actually equal to A bar. So I'll repeat again. So specifically, that is why I interchange B and A such that you write 0, 0, 0, 1, 1, 0, 1, 1. So let us see A plus B. So 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. In both these cases, no carry is generated. But when you do 1 plus 1, the output is 0. But there's a carry of 1 being generated. Okay, a carry of 1 is being generated. Now, we have to see A plus 1. So wherever B is 1, that is in these specific cases, this specific case, we write it. So if you will see, when your input A is 0, A plus 1 is 1. When your input A is 1, A plus 1 is 0. That is why your A plus 1, this is equal to your A bar. Okay, that is why your A plus 1 is equal to A bar. Now, if you look at A plus B, what is the truth table of A plus B? That is equal to A and B bar plus B and A bar. Okay, it is A and B bar plus B and A bar. This is the truth table of A plus B. Okay. Now we have to have one more case, that is A plus B plus 1. So let us look what is that. So you have A, B, C in. You know this is the output Y. So this has zeros. So let us again interchange. You have C in here, A here, and B here. You have 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So, if, and this is Y and this is carry out, C out. This is 0, this is 0. This is 1, this is 0. This is 1, this is 0. This is 0, this is 1. This is Y is 1, C out is 0. This is 0, this is 1. This is also 0, this is 1. This is 1, this is 1. So we are interested, in which case we are interested in the case where Cin is 1 such that this will be equal to, okay, we are interested in that particular case. So what is the truth table? So the truth table which we have to focus on is this. Okay, this is the truth table which we have to focus on. So A plus B plus 1. That is, you have A, B, and this output Y. This is 0, 0, 0, 1, 1, 0, 1, 1. This is 1, 0, 0, 1. So that is why this can be represented as A bar and B bar, or A and B. Okay, it is A bar and B bar, or A and B. Okay. So we have got what does that represent. So A plus 1 is equal to A bar. A plus B is equal to A and B bar plus B and A bar. And A plus B plus 1 is equal to A bar and B bar plus A and B. Okay, and we don't have to consider this case. This case we don't have to consider. This case we don't have to consider. Because the Cn is 0. You only have to consider a case when Cn is 1. Okay, when Cn is 1. So then how do we write it as? So our Y is equal to S1 bar and S0 bar. And what is this? A and B. So your Y1 is equal to A1 and B1 bar. Okay. Then we have S1 bar S0, S1 bar S0, and A1 or B1 prime, the bar. Similarly, then what do we have? We have S1 and S1 and S0 bar. So we have S1 and S0 bar, and that is equal to A plus 1, that is A bar. That is equal to A1 bar. Plus, what do we have? We have S1 and S0, and so we have S1 and S0 and A bar and A1 bar and B1 bar plus A1 and B1. Okay, so this is the representation. Let us expand it. So Y1 is equal to S1 bar and S0 bar and A1 bar and B1 or B1 bar plus S1 bar and S0 and A1 bar and B1 bar plus S1 and S0 bar and A1 bar plus S1 and S0 and A1 bar and B1 bar plus S1 and S0 and A1 and B1. Okay, so this is the value. So now, how do we tackle this? So let us write it again. So let us fully expand it. So this is what S1 bar and S0 bar and A1 bar. Okay, this is this expression. Now let us consider this expression. So this is S1 bar and S0 bar and B1 bar. Okay. Then what do we have? Then we have this expression. So it is S1 bar and S0 and A1 bar and B1 bar. Then what do we have? Then we use this expression. So that is equal to S1 and S0 bar and A1 bar. Okay. Then we have S1 and S0 and A1 bar and B1 bar plus then we have S1 and S0 and A1 and B1. Okay, so why did I specifically write it like this? Now it's become clearer. Sorry. So Y is equal to S1 plus S1 bar and S0 bar and A1 bar plus S1 bar, S0 bar, and B1 bar plus S1 bar plus S1 and S0 and A1 bar and B1 bar plus S1 and S0 and A1 and B1. So that is why Y is equal to S0 bar A1 bar plus S1 bar S0 bar and B1 plus S0 and A1 bar and B1 bar plus S1 and S0 and A1 and B1. Okay, this is the output Y. Okay, so this is how we have found a simplified expression. So this is a bit of a long sum, but it just tries to reinforce the concept of A, like how it is powerful. Then once it is powerful, when you have, how do you generate the circuit? You don't need to specifically have this A and B bar plus B and A bar for everything and all that. How do you route it? You don't need to have a specific circuit, multiple blocks. You can find a simplified expressions and create the circuit with that expression and you can use it. Okay, so this is the power of how do you simplify digital logic Boolean expressions. So let's consider this question. This is the fourth question. So we have to consider an n-bit comparator circuit. So we have, what is that? N-bit, and we are focusing on comparator. Bit inputs A and B. What is the number of combinations for which input A is less than input B? Also find the number of combinations for which input A is equal to input B. Okay. So let us start with a simple 1-bit example. Okay, let us be simple. Let us start with the simple stuff and go. So what do we have? We have A, we have B. We have to find A is less than B, and we have to find when A is equal to B. Okay, so what possible combinations we have? 0, 0, 0, 1, 1, 0, 1, 1. When is A less than B? Is it true here? It is not. It is true here? Yes. Is it true here? No. Is it true here? No. When is A equal to B? It is true? Yes. Then no, no, yes. This is the number of combinations. So how many is the total? You have 1 over here, you have 2 over here. So 1 is actually what? It is, well, let's say 2. This is 2 raised to n. Here n is equal to 1. And here it is 2 raised to n. 2 raised to n by 2. Okay. But let us see what are the possible combinations. This is 1, so this could also be n, right? So let us start with the case. It could be n or 2 raised to n, n or 2 raised to n. So this is coming 2 raised to n. So this is the correct one. Okay, equal to sign can happen 2 raised to n times. What about this? This has 2 raised to n option, 2 raised to 2n minus 2 raised to n, 2 raised to 2n by 2, and 2 raised to 2n minus 2 raised to n by 2. So let us see. So we have so many options. We have 2 raised to n. 2 raised to n is how much? 2, which is not true, right? Next, we have 2 raised to 2n minus 2 raised to 2n, 2 raised to 2n minus 2 raised to n, 2 raised to 2 minus 2, that is 4 minus 2, that is 2. So this is also not true. Then we have 2 raised to 2n by 2. So what is 2 raised to 2n by 2? That is 2 raised to 2 by 2. That is again 2, which is again not true. Then we have 2 raised to 2n minus 2 raised to n by 2. So you have 2 raised to 2n minus 2 raised to n by 2. So 2 raised to 2 minus 2 by 2, that is equal to 4 minus 2 by 2, that is equal to 1. So this is the correct combination. So the correct answer is 2 raised to 2n minus 2 raised to n by 2 is the number of cases when it is less, or the number of cases when it is equal is 2 raised to n. The case for equality. Sorry, so it is n, sorry. Sorry. Okay, so this you can extend to a higher number of bits. That is for your homework. You can check, you can target that. So this is regarding gray code. So as I mentioned, gray code is an unweighted code. Let us try to tackle this question. Let us try. What is 5478? What is its decimal equivalent? This is an octal representation. So in decimal, in binary representation, it becomes 101, then 100, and 111. This stands for 5, this stands for 4, this stands for 7, and this is in binary representation. Now, you have to convert it into gray code, right? So gray code means you will directly take the MSB. MSB you directly take, so you will get 1. Then you will do MSB XOR next one. So 1 XOR 0 is 1. 0 XOR 1 is again 1. 1 XOR 1 becomes 0. 1 XOR 0 is 1. 0 XOR 0 is 0. Then 0 XOR 1 is 1. 1 XOR 1 is 0. 1 XOR 1 again is 0. So this is its representation in gray code. Okay, this is how it looks in gray code. Now, how do we get it into the octal representation? So this corresponds to 7, this corresponds to 2, this corresponds to 4. So this is actually equal to 7248. Okay, which is this one. Similarly, let us try DEC 16. Okay, we have DEC 16. D corresponds to 14, so it is 8, 10, 12, 110. E is 15, so it is all ones. And C is 13, so it is 18101. So this is D, this is E, and this is C. This is binary 2. Now gray code means we directly take the MSB, so this is 1. 1 XOR 1 is 0. 1 XOR 1 is 0. 1 XOR 0 is 1. Right? Then we check 0 XOR 1 is how much? 0 XOR 1 is 1. Then again we take 1 XOR 1 is 0. 1 XOR 1 is 0. 1 XOR 1 is 0. Similarly, 1 XOR 1 is 0. 1 XOR 1 is 0. 1 XOR 0 is 1 and 0 XOR 1 is 1. So this is how, this is the gray code representation. This is in gray code. Now when you have to convert it back to the hexadecimal, so 1001 is 8 plus 1 is 9. 1000 is 8. And 0011 is 3. So this is how it looks in hexadecimal form. Okay. There's some mistake here. There's a B1A. PEC 2, 1, 0, 0, 1, 9. You have to check, but to my knowledge, this is the correct option. This B1A16 is a little bit confusing. Let us check what is B1A16. So what is B1A16? B is 11. So it is 8, 11. 1 is 0, 0, 0, 1. A is 10. 10 stands for 8, like this. This is 2. If you find its, how do you find its gray code? No, it is in gray code and you have to find it to binary. So again, this is the MSB. Then you will take that, what you will take B3 and G2. That means you will take 1 and XOR this. So this is again 1. 1 and XOR with this is 0. 0 XOR with this is 0 XOR with this is 1. 1 XOR with 0 is 1. 1 XOR with 0 is 1. 1 XOR with 0 is 1. 1 XOR with 1 is 0. 0 XOR with 1 is 1. 1 XOR with 0 is 1. 1 XOR with 1 is 0. And 0 XOR with 0 is 0. Okay, this is in gray code. So if you see this would be 1, 1, 0, 1, 8, 9, 10, 11, 12, 13. 13 corresponds to D. This corresponds to E. And this 12 corresponds to C. So DE6, 16. Okay, so these are the correct equivalent representation. Okay. So we'll proceed to the next question. We want to find binary multiplication and find the value of Z. Okay, let us try this. So what we have to do, we have to multiply 1F16 into E16. Okay, and Z, if you see, that also is in hexadecimal. This also is in hexadecimal. But we have to do binary multiplication. So what do we do? 1 is represented as 0, 0, 0, 1. This stands for 1. And F is all 1. This is F. E here all is 0. E is what? 1, 1, 1, 0. This is our E, right? So now we have to do multiplication. It's not just simple addition, it is multiplication. So this is 0, 0, here you multiply, all becomes 0. And these bits you can ignore, right? You can just ignore because it's not going to give you any useful information. Now you have to do with 1, right? So first you will add a 0, then 1 multiplied with it. So 1, 1, 1, 1, 1. Done. Then you'll go for the next one. Okay. So this is again, now you'll add 2 zeros and then you'll do multiplication. So you'll have 1, 1, 1, 1, 1. 5 ones are there. Then you will try with this one. So now you'll have 1, 2, 3. And then again you'll add 5 ones. 1, 2, 3, 4, 5. Now once you have gotten all this, then what do you have to do? You have to add it. You have to add it. So 0 plus 0 plus 0 plus 0, it becomes 0. 0 plus 1 here becomes 1. Here 1 plus 1 is becomes 0 with 1 carry. So this is 1 plus 1 plus 1 plus 1. So 4 1. So this is again 0. And 2 ones get carried over here. So 1 1 2. So 2 3 4 5. So carry and 2 ones. 1 2 3 4 5. So carry and 2 ones. 1, 2, 3, 4, so 0 and 1 carry. So this becomes 0 and a carry. So this becomes 1, 0, 0, 1, 1, 0, 0, 1, 0. So again, what you have to do, you have to group it into 4 combinations. And since this is just 1, so you add 0, 0, 0. So this. So this becomes equal to 2. 1, 1 is 3. And this is 1. So this becomes 132. Okay. So this is how you can do binary multiplication. Let us just check what is the value of this. Okay. Oh. So 1f, this actually is 16 plus 15. So 16 plus 15 is how much? It is equal to 31. And this is, no, 6, sorry, this is, my bad. This is 16 plus 16. Just right over here. 1f16 is 16 raised to 1 into 1 plus 15 into 16 raised to 0. So that is 16 plus 15. Okay, this is 31. Similarly, E16, that is equal to 14. Okay, that is equal to 14. Okay, the issue was here. Okay, let us, the blunder was over here. I'll just rectify it. So what has happened is, when you add all zeros, it is 0. It is 0. When you add only 1, it is just 1. When you add two ones, it is 0 and 1 carry. So that is this 1, 1 plus 1 plus 1 plus 1 here plus 1 here plus 1 here plus 1 here becomes 4 ones. So that is 0. And you will have 2 carry ones. Okay, you will have 2 carry ones. So 1 and 1. 2 carry, third carry, 3 ones, fourth one, 5 ones. So you'll have, because it is odd, so you'll have 1. And then you'll have 2 carries. So 1 here, 1 here. So 2 carries. Again, 1, 2, 3, 4, 5. So 5. So again, you have 1 and you have 2 carries. So 1, 2, 3, 4. Even, so you have 0 and you have 2 carries. So it is 1, 1. So it is 1, 1, 1. So that's why this will actually be equal to 1. And then you'll have a carry 1. So when you add 0 and 1, it becomes 1. So that is why instead of 1011, actually it becomes equal to, what is this, is 8 plus 2 plus 1, so it is 11. That corresponds actually to B. That corresponds actually to B. Okay. So so the multiplication of that is actually 1B2. So it becomes 1B2 16. It's in hexadecimal representation. All right. Now we'll go to the next question. Hamming code. So this is regarding Hamming code. Hamming code, okay, which is in the 7-4 representation. So what have we received in Hamming code? Let us check it, how Hamming code looks like. What Hamming code basically it is, it has your P1, P2, D3, P4, D5, D6, D7. This is the total number of bits and this is the number of data bits. Data bits are represented by D. Okay, and parity bits are represented by P. Okay, so you can, this is like a block, like a register or something. This is how it looks like. Okay, well and good. Now, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. Okay, we have got it. We have coded the positions, binary coded positions. Hmm. The positions have been coded. So how do we generate the parity bits? You have parity bits P1, that is equal to the case when P1 means what? We have 1 here. So where and all is 1 there? In D3 it is there, in D5 it is there, and D7 is there. So P1 is what? P1 is D3 XOR D5 XOR D7. P2 is what? 1 over here. So that is 1 here, 1 here. Then you have 1 here, 1 here. So P2 is equal to D3 XOR D6 XOR D7. Now P4 is what? It has 1 here. So it has D5, D6, D7. So your P4 is D5 XOR D6 XOR D7. Okay, so this is how you generate. This is how you, what you do, you generate parity bits. Generation of parity bits. Okay. Now, once you have generated the bits, you send those data. Like then what do? You send the data. Okay. So let me just tell. So you have the data D3, D5, D6, D7. Then what do? You generate P1, P2, P4. Then you arrange them in that sequence. You arrange it what? P1, P2, D3, P4, D5, D6, D7. Okay? You arrange it like this. Now, you will send this data. Now you send the data. Okay? You transmit the data. Then you will have a receiver. Then it will check. It will, what it will do? It will do error detection. And if possible, it will, what it will do? It will also do error correction. It can also do error correction. Okay, so for correction, what you have to do? For correction, your correction, you will get it as D3 XOR D5 XOR D7 XOR P1. C2 is what? D3 XOR D6 XOR D7 XOR P2. And C3 is what? D5 XOR D6 XOR D7 XOR P3. Okay, that is how you will check the corrected data. So now in our question, what did they ask? This is the information. So the code which we have got is 1011 1011 011 011. So this is your P1, P2, D3, P4, D5, D6, D7. Okay. Let us find C1. What is C1? It is D3 XOR D5. So C1 is, let us do over here itself. So C1 is D3 XOR D5. It is 1. XOR with D5 is 0. XOR with D7 is 1. XOR with P1 is 1. So when there are, so 1 XOR 0 is 1. 1 XOR 1 is 0. 0 XOR 1 is 1. So this is 1. So when there are odd number of ones in the XOR combination, it becomes high. What is C2? C2 is D3. D3 is 1 XOR with D6. That is again 1 XOR with D7. That is again 1 and XOR with P2. That is 0. So again odd number of 1. So this is again 1. C3 is D5. That is 0 XOR with D6. That is 1 XOR with D7. That is 1 XOR with P4. So this is P4. This is C1, C2, C4. So P4 is what? 1. So again 3, 1. So again this is 1. So what does it mean? If at all any of your C1, C2, C4 is 1, that means there is an error. So that's like a red flag. Okay, it's like a red flag. You know, you have alarm bell singing. Okay, so then which position? Now, where has the position of error? Where do you know which bit has got corrupted? How do you know? So that is got by C4 and C2 and C1. So that is what 1 and 1 and 1. So that is what position 7. So that means this guy is the culprit. This guy is the culprit. So instead of 1, it has to be made 0. So the actual correct data which was supposed to be sent or which had been sent but got corrupted was 10111010. This was the information that was sent. And what was the main, the core part of the actual information? This is the entire set of information. What is the data which they actually wanted to send was this. That is your D3, your D5, D6, D7. So the data which they wanted to send, which was actually sent, was 1010. Okay. So this is regarding the Hamming code. How Hamming code is used to detect errors and how it is also used to correct errors. Only one single parity bit can only detect error. It cannot correct errors. It could detect 1-bit error, but 2-bit error also it cannot detect. Okay. It could fail. Okay, so the option is A. Now, we have to find binary multiplication. We have to perform binary multiplication. Okay. First, 17 in 8. How do you represent it? That is 001 and 111. Okay, this is 17. So now we have to first represent everything in binary format. So we have done it. So now what do we have? We have 1, 0, A, 1, B. Okay, and 17 is what? It is 1, 1, 1, 1, 0. Okay, very simple. So now let us start the multiplication. So the multiplication is what? B1, A01. Then what do you have next? You have 0, B1, A01. Then next, what do you have? You have 0, 0, B1, A01. Then you have 3 zeros. Then you have B1, A01. So then you add it. Okay. But they have told the addition value which you are supposed to get has already been informed, already been known, which is 1. Okay, let us write it. That is, it is 1, 0, 0, 1, 1, 0, 0, 1. Then it is again 1, 0, 1, 1, 0, 1, and you have C and 1. So now this has to be 1. If this has to be 1, what does it mean? It means B has to be 1. So what do we got? We got B is 1. Now B is 1, this is also 1. So 1 plus 1 is 0 with 1 carry. So this is 1. So what do we have? We have 3 ones with a carry, but if 3 ones and A. But if it has to be 0, A has to be also 1. So A also actually is 1. So we got A also is 1. So this is 0 and 2 carries. So 1, 1. A is 1, B is 1. So 3 carry means 5. So it is 1 and 2 carry. It is 1, 1, 2, 3, 4, 5. So again 1 and 2 carry 1, 1, 1, 1, 2. And again A is 1. So it is 4. So it is 0 with 2 carry. So 1, 2, 3. So it is 1 with 1 carry. So 1 and 1. This should be equal to 0 and with 1 carry, right? So this is 1. So that means C is equal to 0. So this is how through binary multiplication you were able to find what were the bits A, B and C. Like this is a trick question. Okay. This is how you can get the answer. Okay. So what is this question about? So how many number of 4-bit comparators are required to implement 32-bit comparator circuit? So what is the 4-bit comparator? It has like this. What does it have? It has A0, A1, A2, A3. This corresponds to A, right? Then it will have B0, B1, B2, B3. This corresponds to B. Okay. Then you have it is either greater, it is either equal, or it is less. So you have three options. So you have 4 bits and you have like this. So if you want to get 32-bit comparator, okay, and you only have 4-bit comparator. So how many comparators you would need? You would require 32 by 8, 32 by 4, that would be 8. So you would require 8 such 4-bit comparators to implement 32-bit comparator logic. Okay, at least 8 4-bit comparators you would need. Hmm. So we'll proceed. So which of the following statements are false? We'll have what is true and what is false. So XS3 code is both a sequential and self-complementary code. Yes, it is sequential and self-complementary. Yes, it is true. In ASCII code, B is represented by this and small b is represented by this. We don't know. We'll keep it on hold. XS3 code is 0011 added to BCD. The allowed values are 0011, that is 3 to 15, that is false. So this is false. Gray code is an unweighted code with unit distance. It is also called reflected code, as by reflecting n-1 bit gray code, n-bit gray code can be obtained. This is true. Okay. Binary to gray as well as gray to binary conversion uses XNOR gates. This is false because you actually use XOR gates. Okay. This is not 1111, it is 12. 12 is 1100. This is the limit of this. Okay. This is true. Because what you're doing, you're making 0 to 9, you're making it range between 3 to 12. Now what is 3? 3 is 0011. 12 is what? 1100. So that is how it is, self-complementary. And sequential means it is incrementing. That 0 is 3, 1 is 4, it is same. Okay, so that's how it is sequential and self-complementary. Hmm. So now let's consider this question. Addition in XS3 code. What do we have? We have 415.5 into 10. So how do we represent this? This is actually 0, 1, 0, 0, 0, 1, sorry, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, dot 0, 1, 0, 1. So this stands for 4, this stands for 1, this stands for 5, this stands for 5. Okay. Now, you have to convert to excess 3. So what do you add? You add 1, 3 here. 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. You add it. What do we get? Let us start from here. 1 plus 1 is 0 with a carry. So again, here you have 1 or 1, it becomes 0. The carry. 1 or 1 becomes 1. It again becomes 0 with 1. This is 1, 0, 0. So basically 5 is made 8. Okay, similarly, again, this is another 5. So this again becomes 8. So 1, 0, 0, 0. This again, it is like 1 with 3. So it becomes 4. So this is 0, 1, 0, 0. Right? And this is 4 with 3. It becomes 7. So that is 0, 1, 1, 1. Okay, so what do we get? We get 415.5 that we can represent as 0, 1, 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 0.1000. Okay, this is in excess 3. Similarly, we have 175.11. So 1 corresponds to 4, so that is 0, 1, 0, 0. 7 corresponds to 11, that is what? 8. This 1, 0, 1, 1. 5 corresponds to 8, so that is 1, 0, 0, 0. 1 corresponds to 4, so that is 0, 1, 0, 0. Again, 1 corresponds to 4, that is 0, 1, 0, 0. Okay, this is in excess 3. Now, when we have to add it, we need to make sure that this and this match. There is a decimal point here and decimal point here match. So how do we do that? Okay, so let us write it. So this, we have to convert this to 0. We need to add 0. So this, let me change it. And make this 0. And we need to add 0 plus 3 is 3. So this is 0, 0, 1, 1. So this is its representation in excess 3. Okay, this is how you represent in excess 3. So now let us add them up. So we have 415.5 and 175.11. How do you do it? You have 0, 1, 1, 1. Then you have 0, 1, 0, 0. Then you have 1, 0, 0, 0. Then you have your point. Then you have 1, 0, 0, 0. Then you have 0, 0, 1, 1. Then you have 0, 1, 0, 0. Then you have 1, 0, 1, 1. Then you have 1, 0, 0, 0. Then you have 0, 1, 0, 0. And then you have 0, 1, 0, 0. Okay. Now you have to add them. We have to add. So let us add. So 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 0 is 0. 0 plus 0 is 0. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. The 0, 0, 0, 0. Okay. 1 plus 1 is 0 with a carry. So 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1 again is 0 with a carry of 1. 1 plus 1 is again 0 with a carry of 1. So there is a carry. So this is an important carry. This also is an important carry because it has come from here. This also has come from here. So this is important. When it is within this, the carry, it is fine. But when it goes from one nibble to another nibble, then it is important. So now you have 1 plus 1. Nibble I consider is 4 bits. But the convention we'll have to just check once more. You can clarify. So 1 plus 1 is 0. So it becomes 0. 0 plus 1 is, so then again 1 plus 1 is 0. And then carry of 1. So 1 plus 1 plus 1, 3 ones you add, you have a sum of 1 and you have a carry of 1. So 1 and then 2 zeros becomes 1. So this is the number. So here you don't have any carry. So what is to be done now is, wherever there was a So now you have to have 3. You have to add 3. Okay, you have 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Okay. Wherever there has not been any carry, what you have to do? You have to do subtraction. Here you have to subtract it. Here you have to subtract. And wherever there has been a carry, you have to add it. You have to add it over here. You have to add it over here. Here you have to subtract. Okay. So now let us try to find what will be the result of this subtraction. So here if you see, this will be 1 minus 1 is 0, 1 minus 1 is 0, and 1 minus 0 is 1. Okay. Similarly over here, this how do we do? Let us do step by step. This becomes 0, 10 minus 0, 0, 10. So this is 1, right? Then this becomes 0, this becomes this here, so this becomes again 1, and this is 0, 0. Because it is 8 minus 4, 12 minus 3 is 9. 9, it should be 1, 0, 0, 1. But that is not coming. This part is something we have to check. Let us keep this on hold for the time being. So this is 0 plus 3. So this is your point. This is your important decimal point. 0 plus 1 is 1. Again you add 1. You have 0 and 0. Similarly, here again you have 1, 1, 0 and 0. Here you have to subtract again. This is a very difficult thing because this is basically 12 minus 3. That should be 9. So this again is a question. So let us check this confusing thing which I'm confused about. You can help me out. So this is 1, 1, 0, 0. You have to subtract 0, 0, 1, 1. By common sense, this is actually 12 and this is actually equal to 3. So this should be 9. But let us check why it is not coming. Right? Why it is not coming. So 0 minus 1, how will it be 0? So this is subtraction. Okay. 12 minus 3 is 9. Why is it not being represented over here? Okay, let us assume 0 minus 1, let us say it is 1, and it borrows a minus 1. Yeah, minus 1 and minus 1. So if it becomes, this becomes 0, this becomes 2 minus 1 minus 1, so this becomes 0. 0 minus 0 is 0, and this is 1, 0, 1. Okay, so this is 9. Okay, so this would then be from this. This would be equal to 1, 0, 0, 1, and this would be equal to 1, 0, 0, 1. Okay. So this is the excess 3 subtraction. Oh, let us check it. So you have 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, point 1, 0, 0, 1, 0, 1, 0, 0. There is some error. Error. We're adding over here, adding over here. Why is the value not coming correct? Okay, let us just go for the easier brute force method. We have 415.50 and we have 175.11. Okay, let us say this becomes 1, this becomes equal to 6, right? This 0, 1, 2, 7, 9. Okay, 4 plus 1, 5. So 590.61. Very simple way to represent 590.61 is, this is in 10, let us convert it into binary. So this will into BCD. Let us convert it into BCD. So this is 0, 1, 0, 1. 9 is what? 1, 0, 0, 1. 0 is what? 1, 2, 3, 4 zeros. 6 is what? 0, 1, 1, 0. 1 is what? 0, 0, 0, 1. So this is in BCD. Now to convert to XS3, you have to convert to XS3. Means you have to add 3. So this will what will become? It will become 0, 0. It becomes 0, 1, 0, 0. This will become 1 plus 1, 1 plus, okay, let us, so this is actually 6 plus 3 is 9. So this is 1, 0, 0, 1. This will become 0, 0, 1, 1. This is 9 plus 3 is 12. So it becomes 1, 1, 0, 0. And this is 5 plus 3 is 8. So that is 1, 0, 0, 0. Okay, this is the correct representation. So we had almost got correct. Only there is a slight. So this part is correct. This part is correct. This part also is correct. Only the issue is over here, which has to be checked again. 0, 0, 0, 1, 0, 1, 1 plus 1, 0, 1, 0, 1, 1, 0, 1, 30, 0, 1. Um, mm, 0, 1, 1, 0, 1. Okay, we'll have to check. I'll have to check this. There is some issue, but there's a logic. Like, how do you do? Okay. Okay, so the meeting will end in 1 minute. As soon as it ends, I will again restart the meeting with the same link. So you have to join with the same link. Okay. Okay. So we'll consider this question. So reflected binary code is also known as dash, and it is used for dash applications. So reflected binary code is also known as dash, and it is used for dash. Okay, reflected binary code is known as gray code. Okay, and I check gray slash gray. Both are correct. One is only English, one is American. One is British, one is American, but both are the same meaning. Okay? Don't get worried because of that. And gray code is used for error correction. Okay, gray code is used for error correction. All right. So, which of the following statements are true regarding IC 74181? Okay. Logic. So, which of the following are true? IC 74181 can be connected to IC 74182 to generate look ahead carry for less than 4-bit arithmetic. Yes. The ALU performs bitwise logical operation, and if M is hedged, the ALU performs arithmetic operation. So 2 is true. Which of the following are true? So 2 is true. Wherever 2 is there, we have to be concerned about this. And this also suggests to also answer would be D, but IC 74181 uses ones complement subtraction. Okay, so IC 7481 uses ones complement subtraction. Logic operation is performed by IC 74181 ALU not only includes commonly used NOT, AND, NAND, or NOR, XOR, XNOR, but also all possible functions of two variables because it has 16 logical operations, and if it has two variables, it can do 2 raised to 4, that is 16. Okay. Mode select input M. If M is low, then ALU performs actually arithmetic operation, and if M is high, then it performs ALU operation, arithmetic operation. Right? Okay, let us look at this complicated question. Mhm. Okay, let us consider this. Okay, y0 is 0. No, y0 is 0. Y1 also is 0. Y2 is 1. Y2 is 1 and Y3 is 1. Okay. So x0 and y1. What is x? So this is what? 1, 0, 0, 1. So 1 and 0, 0. So this is 0. Hmm? X0 and y1. The x0 and y1 is x0. What is x0 is 1 and y1 is 0. So this also is 0. So this also will be 0. This also will be 0. This also will be 0. X1 and y0. Y0 also 0. So this also 0, 0, 0, 0. So 0 or 0 is again 0. Carry will also be 0. So all are 0, 0, 0, 0 over here. X0 and y2. What is x0 is 1. Y2 is 1. So this is 1. X1 and y2 is 0. And what do you have is x2 is 0 and y2 is 0. So it is 0. And x3 is 1 and y2 is 1. So this is 1. Okay, this is 1. Now 0, and when you add 0 and 1, this will become 1. The carry will be 0, right? Then 0 or 0 is again, you have 0, and this is 0. 0 and 0 again is 0. And you have 0 here. 0 and 1, you add 1, it becomes sum is 1, carry is 0. Okay, so you have 0, 0, 1, 0. Now x0 and y3 is what? X0 and y3, so this is 1. X1 and y3 is 0. X2 and y3 is again 0. And x3 and y3 is 1. So the combination which you will get is 0, 1, then you have 1, 0, then you have 0, 0, and you have 0, 1. So let us check the solution. It is 0, 1, 1, 0, 0, 0, 0, 1. Okay, so the option is C. Correct option is C. Okay, so basically here you're doing 4 into 4-bit multiplication, and this is a combinational circuit. And why are you using this combinational circuit? Like what it is made up of? Repeated additions. and you're using what appropriate connections. And you need to take care of the carry which is generated. So in some cases you have a half adder because a half adder is sufficient. In some cases you have a full adder. So these are the various possible combinations. Okay, so let me do a recap of what was considered. So one we checked with sir taught this week was magnitude comparator. That is, we have to find which is greater or less than. Okay, kind of like checking the balances. Then you have an arithmetic logic unit. So this is a an IC which can perform multiple functions. Then you have error correction and detection. When you do transmit the bits and you receive the bits, you know there could be an error. To detect error, you can use parity bit, but that is limited to only one bit detection. It is limited to only one bit error detection. It can only detect, but if you want to correct it, you need to use that Hamming code, etc. So that was also taught by Sir. Then unweighted codes. We have various unweighted codes, that is gray code. You also have what is XS3 code. Then you have ASCII code. Okay, when you press the keyboard or when you click the mouse, when you press the keyboard, whichever button you click, depending on that, it will generate some certain code. Okay, that is used. So that is used for the processing. So that is known as ASCII code. Then binary multiplication and division, which is basically repeated addition and repeated subtraction. So that is the circuit. So this what Sir taught this time was a combinational circuit. Combinational circuit. And Sir told that further on he will teach in the course sequential multiplication and addition, which is more, easy, more resource friendly and better. Okay. This combinational circuit is like a brute force, big, bulky circuit, but a sequential circuit is much more simpler. It's more logical as well. So, what is a magnitude comparator? Why do we need a magnitude comparator? You have to compare two inputs. Okay, so A and B, these are your inputs. You will be comparing them, and you'll have either it is greater, it is equal to, or less. So, subtraction of A and B, you could either use what method? You could either use the method of subtraction, where you will subtract, and depending on the LSB, the MSB, you will say whether it is negative or positive or it is equal. Okay, but it has certain limitation, and you're using more resources. You're using more resources because you have to have this entire subtractor circuit, which is not actually your objective is not that. You have a goal. For the goal, you can have multiple methods, but as you're learning, as you're engineers, as you're trying to understand, the objective of this course is you're trying to find the optimized, resource friendly circuit that can perform your function. That is the objective. You can make a very complicated circuit which can do this, but the goal is you have to find the smallest, most efficient, reliable, error free, or robust circuit which can get you your output in a repeated manner. Okay, so that is why we have subtraction. So that's why we have this comparator. You could have a greater, it could be equal, it could be less than. So there are three possible things. Input is either equal, the inputs are either equal. One input is greater than the other input, or one input is less than the other input. Based on that, you can get these outputs. Then when you increase the number of bits, okay, it's no longer just one bit. You have to increase, you have to scale it up. But what you do is you cascade it. That is, you consider you have only one bit. You have a one bit comparator here. You have another one bit comparator here. And you're using both these one bit comparators to build a two-bit comparator. So you're using, modules. You're using one module of one bit comparator, using another module of one bit comparator, you're combining them You're appropriately making the connections and you're effectively then generating your effective output. So it is a combination of modules. So your one bit adder, one bit comparator is tested, another one bit comparator is tested. Then you combine them, okay, and then you appropriately combine them and make your overall 2-bit magnitude comparator. Okay. So then also we have an arithmetic logic unit. So this is a circuit. This is your arithmetic logic unit. These are the various inputs you have. You have various inputs you have. These are the various select lines. These are the various outputs. Okay, depending on the select lines, you will select whether this function will happen, whether the next function will happen, and so on and so forth. Okay, you could have a plus b, you could have a plus b plus 1, and so on. You could have arithmetic operations. You could also have logical operations. So it's kind of like your mini computer. It's used for arithmetic operation, used for logical operation, and so on. Okay. Then you have unweighted codes. Unweighted codes can be gray code. It could be XS3 code. It could be ASCII code. What happens in the normal binary code is many bits change. When you have multiple bits changing, there could be a possibility of error. So what is done is it is implemented in gray code. You convert it into gray code. Gray code is a sort of reflected code. It's a code where you try kind of reflect. You make it, you reflect it, you change it. And for generating gray codes, you use XOR gates. XOR gates are utilized for generation of gray code. Next is you have BCD numbers, which are very popularly used. Now, when you have BCD numbers, it is difficult to do the addition subtraction. So what is done is it is made into XS3 code representation. It makes it easy for you to add and subtract. And so what do you do is for the BCD representation, you add 3 and you represent it. That is the XS3 representation. Then also we talked about error correction, error detection and correction. You have to detect if an error is there. You have sent a set of bits. The advantage of digital is errors are less because you either have it high, low, high, low, high, low. But still, in practical reality life, there's always corruption. There's always deception. So the bit could get changed. So if the bit has changed, how do you detect? First of all, you have to detect that there was an error. You have to make sure you have to you check for that the concept of parity was introduced. Okay, the concept of parity was there. It could be either odd parity you could send, or you could send it as an even parity. So if the parity of the bits is not correct, then you can add a parity bit to change it into the correct odd or even parity. That all is there. But even though you do all that and you send the data, still while sending the data could get corrupted. So parity could check if one bit is corrupted. It could tell you. It could give you an indication that an error has occurred, but it will not tell you that which bit the error has occurred. It can also not correct, and it can also not detect if more than 2 bits have got corrupted. If 2 or more bits have got corrupted, it can also not tell you that which location, and it can also not help you to correct the error. So to do that, there was a Hamming method. A Hamming theorem was there. It found out what is the Hamming distance and how much is required, how much correction is possible based on the Hamming distance, and so on. So those are there. So how do you insert those number? What you do in Hamming is you add more parity bits and you insert them at appropriate locations. And through that and through processing of those parity bits and the data bits, you can know whether your data is correct or not. Okay. Then you have binary addition, you have multiplication, which is repeated addition, and binary division using subtractor circuit. So then we consider the questions that how a very simple circuit, if you really need a very, very simple, fast, you need to know whether they're equal. Whether you have to check equality, then you can use what is known as an XNOR gate. You can use an XNOR gate to check whether they are equal. Right? Then how you use a combination of half adder. So you know this concept of half adder, full adder, they're like the building blocks. So you need to know this truth table of half adder and full adder well. You need to know what is the carry, what is the sum, what is the truth table. and then it will help you, it will ease your speed and improve your speed of solving sums and accuracy as well. Then there's a big complicated question regarding arithmetic logic unit ALU, where there's a truth table also is provided. So it's good to read the question properly, see what information is there, how that the outputs y0, y1 they are independent. That is, you do bit wise operation. Okay, and you have a plus 1, a plus b, a plus b plus 1. So what do they mean? So to do that, what I did was I found out what is the truth table. What is the truth table of a plus b? And we found out that truth table of a plus b is a and b bar plus b and a bar. That is basically just an XOR gate. Then a plus 1, it comes out to be a bar. Okay. Similarly, when you have a plus b plus 1, so this is what? This is a plus b plus 1. This is our output. And that is actually equivalent to your XNOR gate. Okay, XNOR gate. That is a bar and b bar plus a and b. All right. And then we combine the overall, the logical expression which we get. We use the minterm based representation. And then you can use certain, what you known as Boolean algebra to simplify. Boolean algebra for simplification. Okay. So this is the overall simplified expression which is obtained. So you don't need to, make individual blocks and then add a select line and then do the anding of that. You can simplify. So you can simplify, and this actually is not y, it is y1. This is your y1. Okay. So you can get a simplified expression. So the objective is, you have to simplify the number of gates, the number of transistors, etc., to make a optimal circuit with less power consumption, more reliability, cheaper, and smaller size, compact, all that. So that is why we have to, go to the grill and simplify, find out the common terms which can be used for different outputs. Sort of talk about minimization of gates and so on. The optimization, all these things. Okay. Then we have an n-bit comparator. What is the number of combinations when a is less than 1, a is less than b, or also the number of combinations when input a is equal to input b? How do you know? How do you know? So for that, if I go for an n-bit, it is a complicated. So let us start with a simple 1-bit example. 1-bit example, what do we see? That a is less than b occurs only once, and a equal to b occurs twice. So accordingly, based on the multiple choice question it is, which had multiple options. So this was simple. This was 2 raised to n was simple. But this had multiple options. So we iteratively, you check this option, this option, this option, and found that this option is correct. So these are the number of combinations when it is less, and these are the number of combinations when it is equal. Now we converted gray code conversion of this. Is a gray code conversion. Similarly, we also consider binary multiplication, and we have to find the value of z, which you got in 1b2. You have to be very careful in the carries which you do. Don't make the errors like how I make. Then we had a question about Hamming code, where how we showed how Hamming code can detect the error. It can pinpoint which bit has gone wrong, and once it pinpoints which bit has gone wrong, it can help you to correct the error. Okay, it will tell you what is the location also of the error. Okay, so this is the power of Hamming. How do we generate this P1, P2, P3 parity bits? And then when we send the data, how do we, add it, and, the location of the parity bits and the data bits? This is all important. Okay. And then how do we, check what is the error detection circuit? This is the circuit which has to be used for error detection. And how do we find the position of the error? And then which bit has to be then inverted, because it is 1 or 0. It is, if it was supposed to be 0 but it became 1, then what do we have to do? We have to just invert it. So accordingly, it will do it. Okay. Similarly, binary multiplication was done to find the values of the bits. Okay, what are the bits we need to find the values? A, B, and C. And these are the bits for which we needed to find the values, right? Then if you, how many number of 4-bit comparators are required to implement 32-bit comparators? So what do we do? We did 32 divided by 4, that is 8. So we need 8 combinations of 4-bit comparators to implement a 32-bit comparator. But it could be done in a serial fashion, serial or cascaded fashion, or it could be done in a multi-level fashion as well. Both combinations are possible. Okay. Then we had a question regarding true or false. It described, the various unweighted codes. So this question is basically for unweighted codes, right? Basically regarding that. Then we had to do subtraction and addition in XS3 code. Since it's just an MCQ, you can just add it up and get the value and then represent it in XS3. So you have to first represent it in terms of XS3 and then you add it and you subtract it and get the output. Hmm. And then we consider what is the reflected binary code, what is gray code, and it is used for error correction. And gray can have multiple spellings, both spellings are correct. And how you do repeated addition, how do you use the AND gates, how do you find the logic? Since it is AND gate, if it is 0, this whole row would be 0, this is 0, again whole row is 0, 1. You check which is the half adder, full adder, whichever adders have to be utilized, and then you can get the output. Okay. Okay, so this is how we consider the various things about week 6. So thank you for joining. See you again for next class. Okay, thank you. Good night. Bye.